Please subscribe to support the channel. Why does something with no mass slam into a speed limit instead of moving at any speed at once? You're told again and again that light in a vacuum has zero rest mass, but its speed is locked at about 300,000 kilometers per second. Not very fast, but a fixed number. It never comes out a little higher or a little lower. That's already telling you something important. This is not about how strong your flashlight is or what kind of star the light came from. This is about how reality itself is set up. You might think, if there is no mass, there is nothing to resist motion, so why not infinite speed? That sounds simple, but it's based on an everyday picture that assumes space is just a three-dimensional stage and time is a separate universal clock. In that picture, you could imagine dialing up the speed of a massless thing without limit. But the moment experiments show you a hard maximum speed, that picture is in trouble. Light is not the weird exception, your starting assumptions are. So how do we know this cosmic speed is really that strict and not just something that roughly holds near Earth? Take a real event. In 1987, a massive star in a small companion galaxy of the Milky Way exploded as a supernova. The light from that explosion spent around 168,000 years traveling through almost empty space before it reached Earth. If the speed of light in vacuum could drift even slightly, you might expect that over that huge distance, the effective speed would be different from what we measure in the lab. But when astronomers recorded that light, its behavior matched the same speed we measure with equipment on Earth. Light from distant galaxies, radio pulses from spinning neutron stars, and many other signals all give the same result. You take the distance, divide by the travel time, and you get basically the same value every time. That means the universe treats this speed as a constant rule, not a local detail. So the question gets sharper. What is forcing that number to be the same everywhere for everything? So what happens when you try to apply your normal rule that speeds simply add? If you're walking inside a plane, someone outside adds your walking speed to the plane speed to get your total speed. That rule feels automatic because at low speeds, it works extremely well. So it's natural to imagine doing the same with light. If a ship is moving and someone on the ship shines a beam forward, maybe the speed of that beam seen from outside should be ship speed plus light speed. When people tested that idea, it failed. Over and over, experiments showed the same thing. Measure the speed of light in a vacuum and you always get the same answer, no matter how you're moving. The classic example is when light beams are sent in different directions while Earth is moving around the sun. If there were a simple fixed background and speeds really just added, you'd see tiny differences between the beams. You don't. Your usual rule for adding speeds turns out to be a good low-speed approximation, not a fundamental law. So if speeds do not combine the way you thought, what is really special about this one speed that refuses to change? The next step came from a place that, at first, didn't look like it was about light at all: the study of electric and magnetic fields. In the 19th century, physicists worked out the rules for how electric charges push and pull on each other, and how changing electric fields create magnetic fields, and changing magnetic fields create electric fields. When they combined those rules into one system and asked, if you disturb the electromagnetic field in empty space, how fast does that disturbance move? The math did not say any speed you like. The result was very specific. The equations allowed waves in the electromagnetic field only at one particular speed. And that speed was determined entirely by two quantities you can measure in a lab: how strong electric forces are in vacuum and how magnetic fields respond to changing electric fields. When they put the measured values of those quantities into the calculation, the speed that came out was the same as the measured speed of light in vacuum. That was a big moment. It said two clear things. Light is an electromagnetic wave, and the laws of electromagnetism already contain a built-in preferred speed. Nobody picked it by hand. It's fixed by how the fields themselves work. So now you have two facts that support each other. First, experiments say all observers moving at constant speeds measure the same value for the speed of light in vacuum. Second, the field equations that describe electricity and magnetism say electromagnetic waves must travel at one specific speed, set by constants of nature. That's strong evidence that this speed is not just some random feature of photons, but a basic feature of how space, time, and fields fit together. But this still leaves the key tension right in front of you. If light has no rest mass, why is it locked to that speed instead of being allowed to move faster or slower? Why is there not a whole range of allowed speeds for massless stuff? Why is there a limit at all? And why do all our experiments and all our equations agree on the same value for that limit? The answer is going to force you to stop thinking of this as the speed of light and start thinking of it as the maximum speed at which any influence can travel. To reach that, you have to change how you think about time, distance, and motion themselves. You have to accept that the usual picture of a universal clock and rigid space is wrong at a basic level, and that space and time are tied together in a structure where this speed is the conversion factor between them. That's the step Einstein was pushed into by the data. So the real question we now have to attack is this. If this speed is woven into the structure of space-time and into the laws of fields, exactly how does that force every massless particle to move at that speed? And why does it forbid anything with mass from ever catching up? That's where we go next, when common sense collides with experiment and Einstein has to rebuild the rules from the ground up. How do you kill the idea of an invisible substance that everyone thinks must exist, using nothing but a couple of light beams and some patience? For a long time, physicists were sure that light had to travel through some medium like sound needs air. They called it the ether. Earth, they thought, was moving through this ether as it orbits the sun. So if you send one beam of light along the direction of Earth's motion and another beam at right angles, common sense says their speeds through the ether should be slightly different. One beam is going with the ether wind, the other is mostly sideways. The Michelson-Morley experiment was built exactly to test this. They split a beam of light in two, sent the two parts along perpendicular paths, bounced them off mirrors, and brought them back together. If one beam had been slowed down even a tiny bit by the ether wind, the timing difference would show up as a shift in the interference pattern when the device was rotated. They tuned it to be insanely sensitive. The expectation was not, maybe we'll see something. They were sure they would. The result was basically nothing. Rotate the whole setup, run it at different times as Earth orbits the sun, repeat and repeat. No shift. The speed of light looked the same in all directions. That killed the simple picture of an ether you could move through like air. It also smashed the idea that you could just add your motion to light's motion in a straightforward way. If Earth was really plowing through a medium, you should see light behave differently along and against that motion. You don't. So the old background frame, where speeds add in the obvious way for all things, failed an extremely direct test. That raised a sharp question. If light doesn't care about our motion through space, what is setting its speed? The next punch came from theory, not experiment, and that's even more uncomfortable. When James Clerk Maxwell wrote down the combined laws of electricity and magnetism, he didn't start by talking about light at all. He started from lab facts: how charges attract and repel, how currents make magnetic fields, and how changing electric fields create magnetic fields, and how changing magnetic fields create electric fields. Pack all that into one set of equations, ask what happens if you disturb the electromagnetic field in empty space, and you find that ripples in that field must travel at a specific speed. Here's the key point. That speed is not a free parameter. It is fixed by two constants you can measure separately in the lab. The one that tells you how strong electric forces are in vacuum, and the one that tells you how strong magnetic forces are. When you combine those two constants in a certain way, the result has units of speed. You calculate that speed from their measured values and you get roughly 300,000 kilometers per second. That is exactly the same as the measured speed of light. So from pure field theory, without talking about light beams from stars or lamps, you already get a built-in propagation speed for electromagnetic waves. Then nature tells you that light is one of those waves. That is not luck, it is a huge clue. It says the universe contains a preferred speed baked right into the equations that govern fields. So now you have experiments saying everyone measures the same speed for light, and you have field theory saying there is one special propagation speed determined by the constants of electromagnetism. That forces a much harder question. How do you build a picture of motion where that speed is the same for everyone, instead of behaving like normal velocities that just add? Einstein's move was to stop fighting the data and accept two simple statements as starting points. First, the laws of physics are the same for all observers who are not accelerating. In other words, no constant velocity frame is more correct than another. Second, when you measure the speed of light in a vacuum in any of those frames, you always get the same value. From those two assumptions, and from the requirement that the equations of physics keep the same form in all such frames, he found that something has to give in your basic ideas of time and distance. The place that breaks is not the speed of light. It is your assumption that time is absolute and the same for everyone. To keep light speed fixed for all observers, the conversion between space and time measurements has to change depending on how fast you are moving. That means different observers do not agree on how long events take or how far apart they are once their relative speeds are high enough. That sounds crazy until you look at real phenomena that only make sense with this new rule. Consider unstable particles called muons created high in Earth's atmosphere by cosmic rays. In their own rest frame, they live for a very short time before decaying. If you multiply that lifetime by the speed of light, you get the distance they could travel before decaying if they were moving at close to that speed. With classical ideas, that distance is too short for most of them to make it down to the surface. But we detect large numbers of them at ground level. The explanation is not that something is wrong with the decay time or with the speed measurement. The explanation is that in our frame, the moving muon's internal clock is running slower than a clock at rest next to us. This effect is called time dilation. The faster an object moves relative to you, the more its elapsed time shrinks compared to yours. Fast-moving particles live longer from your point of view. Their internal processes are slowed down. This is not just a story. It is measured in particle physics experiments and in precision tests with fast-moving clocks. It is exactly what falls out of Einstein's assumptions when you force the speed of light to be the same in all inertial frames. Once you accept that time can no longer be universal, you are pushed to an even stronger statement. The real rule is not light has this special speed, but there is a maximum speed for any interaction or information, and its value matches the speed of light. Light is not choosing that number. The geometry of space-time and the structure of the field equations together demand that there is a highest possible signal speed. Massless particles are forced to move at that speed. Massive objects are forced to move below it. The whole theory of special relativity is built around that limit. So the real villain, from the point of view of your everyday intuition, is not light itself. The real villain is relativity, the idea that space and time form a single structure and that the laws of physics must look the same in all constant velocity frames. Those requirements leave no room for light to speed up or slow down in vacuum. They also leave no room for you to accelerate a massive object all the way to that limit. Change the limit, and the whole structure of the equations collapses. That sets up the next layer of the puzzle. If relativity and the field equations enforce a top speed, how exactly do they tie that to energy, momentum, and mass in a way that locks massless particles at that speed and forever keeps massive ones below it? In other words, how do the rules of the game in momentum and energy space make stuck at the limit and never reach the limit happen at the same time? How can something have no mass but still hit you like a hammer in the equations? You've heard the famous line that energy equals mass multiplied by the square of the speed of light. That sounds like if mass is zero, energy should also be zero. But that is only the simplified version for an object sitting still. The full rule in relativity ties three things together at once: energy, momentum, and mass. In words, if you take the total energy of a particle, square it, and divide it by the square of the speed of light, you get a sum of two parts. One part is the mass term, and one part depends on the square of the momentum. That means energy is not just mass turned into energy. Motion matters. Momentum is the quantity that measures how hard something is to stop, and relativity says energy and momentum are locked together.
For a particle with zero rest mass, like a photon, the mass term drops out of that big relation. What is left is simple. The energy is directly proportional to the momentum multiplied by the speed of light. No mass, but still momentum. No mass, but still energy. So a photon is not a ghost. It carries real punch in the equations, and that punch shows up in the real world.
If that sounds abstract, here is a concrete test. Can light push on things the way a stream of tiny bullets would? With lasers, the answer is yes. Photons carry momentum, so when a beam of light hits a surface, it transfers a tiny shove. If the light is absorbed, it gives one amount of momentum. If it reflects, it gives about twice that, because the direction reverses. In the lab, this is not just a cool idea. It is a measurable effect. Sensitive setups can see mirrors move under the pressure of light. Devices called optical tweezers use focused laser beams to trap and move microscopic particles only by the momentum of photons. Now stretch that idea out into space. If photons carry momentum, then in principle you can build a sail that they push on. A light sail is just a very large, very thin reflective sheet. Each photon that hits and bounces off transfers a tiny bit of momentum. One photon does almost nothing, but a constant flow from a star or from a powerful laser adds up. The force is small, but it is steady. And in space, you do not have air drag or friction fighting you. Over time, a spacecraft pushed by light could reach very high speeds. This is not fantasy anymore. Small-scale missions are already testing light sails in Earth orbit. The only way this works is if photons really obey that energy momentum rule and really carry momentum despite having zero rest mass. The universe uses the same trick on a much bigger scale inside stars. In a very bright star, radiation coming from the hot, dense core is constantly streaming outward. Those photons are not just lighting the place up, they are pushing on the star's outer layers. Gravity is trying to pull everything inward, compressing the gas. Radiation pressure from light is pushing outward, fighting that collapse. There is a specific brightness, often called a limiting luminosity, where the outward push from radiation pressure almost exactly balances the inward pull of gravity. If a star gets too bright for its mass, radiation can start driving material off its surface. That limiting brightness depends directly on how much momentum the light carries per unit time per unit area. In other words, it depends on that same energy is proportional to momentum times the speed of light rule for photons. Change the way photons carry momentum and you change how stars live and die. So by the time you get to stellar physics, the idea that massless still means momentum is not a minor detail. It is a major control knob on the structure of the cosmos. So how does this connect back to the speed limit? The full energy-momentum relation in relativity does more than just say photons have energy. It also tells you how speed behaves for different masses. For a particle with non-zero mass, as you pump in more and more energy, both the energy and the momentum grow. But the speed does not just keep climbing linearly. It gets closer and closer to the speed of light, but never reaches it. The math gives you a speed that approaches the limit as an asymptote. Every extra chunk of energy moves you a bit closer, but there is always some gap left. To actually hit the speed of light, a massive particle would require infinite energy. That is the formal way of saying not going to happen. Now look at the special case where the mass is exactly zero. In that case, the mass term in the energy-momentum rule is gone, and you're left with a much simpler link between energy and momentum. If you then work out what speed this corresponds to, you find that the speed must be exactly equal to the cosmic limit. Try to make a massless particle move slower than that speed, and the numbers in the relation no longer match up. You would be trying to assign energy and momentum values that cannot satisfy the rule. Try to make it move faster, and you are again breaking the same relation. For zero mass, the only consistent speed is the speed of light. So massless is not a free pass. It is a hard constraint. Massive particles are forever stuck below the limit, no matter how much energy you feed them. Massless particles are nailed to the limit itself and can never slow down without ceasing to exist as the thing they are.
That is why you never see a photon at rest. A photon at rest would be a photon with energy but no momentum and zero speed, and that simply does not fit the energy-momentum rule that everything else obeys. This also means photons are not loose, independent actors choosing their speed in some empty background. Their lack of rest mass forces them to live exactly on the boundary defined by spacetime structure and by the energy-momentum law. They are locked to that special speed and can only change direction or energy, not their basic travel rate through empty space. When you see a beam of light, you are seeing excitations of a field that are stuck on the edge of the allowed region in the energy-momentum map. So, you now have three layers all pointing to the same conclusion. Relativity sets a maximum signal speed in space-time. The electromagnetic field equations pick out a specific numerical value for that speed. The energy-momentum relationship then says, if your mass is non-zero, you can only approach that speed from below. If your mass is exactly zero, you must move at that speed and no other. That is why photons are not free to go faster. Masslessness is not freedom. It is a hard constraint. This raises the next, deeper question. If the speed limit is wired into space-time and into energy and momentum, how does it show up in the actual map of which events can affect which others? How does this one number draw a boundary in space-time between can ever be connected and forever out of reach, not just for light, but for any cause and effect? How far out into the universe can you actually touch if you start right now? Not in a poetic sense, in a strict physics sense. What regions of space-time are you allowed to affect, even in principle? Relativity gives a very blunt answer. Draw a boundary around your here and now, and that boundary is set by the speed of light. Not your rocket power, not your imagination. One number. Picture this. Fix one event, you, in one specific place, at one specific instant. Now ask, if I emit a flash of light right now, where could that light reach as time moves forward? All the possible positions that flash could occupy at later times form a kind of expanding shell in space. If you stack those shells for every possible time into a space-time diagram, they form a cone opening into the future. That region is called your future light cone. Any event inside that cone is something you could, in principle, influence, because a signal moving at or below light speed can get there. Flip the story. Ask which past events could have sent a light signal that reaches you exactly now. Those form another cone, pointing into the past. That past cone contains everything that could have ever affected you by ordinary cause and effect. Something outside that past cone cannot have gotten information to you in time, no matter how advanced the technology, as long as it respects the cosmic speed limit. So your entire causal life is trapped inside these cones. They define what reachable and in contact even mean.
So where does this cone structure actually come from? After Einstein, Hermann Minkowski took the ideas of relativity and rewrote them in geometric language. The key move was to stop treating space and time as totally separate. Instead, you treat them as parts of one four-dimensional structure, three directions of space, one of time. To make that work, you need a way to measure distance between two events that mixes space and time in a specific way. In everyday space, you might say the distance between 2 points is found by taking the differences in their coordinates, squaring them, adding those squares, and then taking the square root. Minkowski's version says you must combine the square of the time difference after converting it into a distance by multiplying by the speed of light, and the square of the spatial separation, but you combine them with a minus sign between the time part and the space part. When you do that, you get a single quantity called the space-time interval. Here is the crucial bit. For light, this space-time interval is exactly 0. The time difference multiplied by the speed of light squared is exactly equal to the squared spatial distance the light covers. In this geometry, that is what moving at the speed of light means. You travel along paths where the space-time interval is 0. Events that can be connected by light sit on the surface of those cones. Events that can be connected by slower signals sit inside the cones, where the time part dominates. Events outside the cone are separated in a way that forbids any influence traveling at or below light speed from connecting them.
That already tells you something important. This structure is not specifically about photons as little particles. It is about which pairs of events can be causally linked at all. If you have any signal that carries information, photons, neutrinos, gravitational waves, particles in a beam, it must follow a path that stays inside or exactly on the light cone. A massive particle always stays inside, a massless one rides the surface. If you imagine a signal that goes faster than light, you're talking about jumping outside the cone. That would mean the space-time interval between the send event and the receive event has the wrong sign. In this geometric language, that sort of separation is called space-like. It means the spatial distance is too large for the time difference to allow even light to cover it. Connect those events with a real signal, and you're trying to wire together parts of space-time that the geometry says should be causally separate. This can sound abstract, so let's drag it straight into technology you use every day. GPS. Your phone's position comes from talking to satellites that orbit Earth with atomic clocks on board. Those satellites are moving fast compared to you on the ground, and they're higher up in Earth's gravity well. Special relativity says moving clocks tick slower. General relativity says clocks higher in a gravitational field tick faster. Both effects are real, and both are measured. Engineers building GPS have to account for these shifts. If they didn't, the timing used to infer distances from satellite to receiver would drift. The position errors would grow by kilometers per day. The system would basically fail. Instead, the design of GPS uses the space-time interval idea in practice. It treats time differences and spatial distances as linked through the speed of light. Signals from the satellites are assumed to move at light speed in vacuum, and the timing is corrected for the relativistic effects predicted by the space-time geometry. When you see your map app lock onto your location within a few meters, you are watching Minkowski geometry and the light cone structure doing their job. So when you ask, why can't light go faster? You're really asking, why can't the boundary of those cones tilt in more? If light could move faster, the surface of the light cone would be steeper in a space-time diagram. That would drag more events inside your causal reach. At first, it might sound great. More things can talk to more other things. But relativity says different observers moving at different velocities slice space-time up into space and time in different ways. Because of that, if you allow signals outside the cone faster than the current limit, then some observers will see those signals as going backward in time. The order of cause and effect would not be the same for everyone. You could arrange situations where, in one frame, event A causes event B, but in another allowed frame, B happens before A. That is not just a weird viewpoint issue, it means the basic idea of a consistent chain of cause and effect breaks down. So the speed of light in vacuum is not just how fast light goes. It is the slope of the boundary between can be linked by a cause and never can be linked by any cause in spacetime. The cones define all allowed influence. Massless particles hug that boundary. Massive particles stay safely inside. Nothing physical is allowed to cross out into the forbidden region. If something did, spacetime's causal map would stop making sense. That's the real logic behind the speed limit. It is a geometric statement about which events can ever touch each other. Light cannot go faster because that would mean ripping open the causal structure itself. And the universe, so far, behaves as if that structure is non-negotiable. But saying the geometry forbids it is still a claim. You need hard checks that nature actually respects this map in detail, from tiny lab setups to cosmic explosions. If C is truly the ceiling for any influence, you should see it show up in precise timing tests, in particle accelerators, and in signals that have been traveling for billions of years. So the next step is simple and brutal. Time the fastest things we can find and see if any of them ever, even slightly, beat the limit. How do you prove a cosmic speed limit is real and not just clever talk with nice diagrams? You hit it from every angle you can think of. Short distances, long distances, different energies, different particles, and different directions. And you keep asking the same blunt question. Does anything ever outrun this number, even by a tiny amount? Start small. In the lab, you can send super short laser pulses down a known distance and measure how long they take to arrive. The distances can be a few meters or tens of meters inside carefully controlled vacuum tubes or optical paths. The timing electronics can see differences of trillionths of a second. That is 1,000 billionths of a second. At that resolution, if light speed in vacuum wobbled even a little with time of day, with direction, with color of the light, you would start to see it in the distance divided by time. What actually happens is boring in the best possible way. You measure, you repeat, you change the setup, you improve the equipment, and you keep getting the same value within the tiny error bars of the instruments. That number is not drifting around. When people publish these measurements, they quote more and more digits, but the central value is stable. Those controlled tests give you confidence that over human scales, the speed of light in vacuum is not some approximate average. It is a precise constant. Now, short-distance tests are nice, but they only test one kind of possible violation. Maybe you could say, light behaves differently at extremely high energies or over extremely long distances. That is where nature hands you something much bigger: gamma-ray bursts. These are violent explosions in distant galaxies that send out photons across a huge range of energies, from relatively soft gamma rays up to extremely energetic ones almost at the same moment. Those photons then travel for billions of years before hitting our detectors. If higher energy photons had even a slightly different vacuum speed than lower energy ones, the timing differences at arrival would stretch out. A tiny difference in speed over billions of light years becomes a big difference in arrival time, seconds, minutes, or more. So astronomers look very closely at the arrival times of different energy bands from the same burst. Over and over, what they see is consistent with all those photons sharing the same vacuum speed once you account for how the burst itself emits them. If there is any energy dependence hiding there, it is below very strict limits. That is a long baseline check. Different energy, massive distance, same limit. Then there is the famous supernova from 1987 in that small neighboring galaxy we already talked about. When that star collapsed and exploded, it didn't just release light, it also released neutrinos, those very weakly interacting particles that almost never hit anything. Detectors on Earth saw a burst of neutrinos a few hours before the visible light from the explosion arrived. At first glance, that can sound like the neutrinos traveled faster than light. Here's where you have to be careful and keep track of what happened inside the star. The neutrinos were produced in the core collapse and basically passed through the star's outer layers almost freely. The light, on the other hand, was generated and scattered inside that dense environment. Photons bounced around, were absorbed and re-emitted, and had to fight their way out of the material. That takes time. So the delay is not a race in vacuum, it's a delay inside the star. Once both the neutrinos and the light are out in empty space and traveling toward Earth, the arrival times are consistent with both moving at essentially the same cosmic speed limit, taking into account small differences in the exact emission times. If neutrinos had really had a higher maximum speed than light in vacuum, the difference after 168,000 years would have been far more dramatic than a few hours. You don't see that. So even across galactic distances, different kinds of nearly massless particles are obeying the same limit.
Now look at particles with mass in a place where humans are pushing them as hard as possible. Particle accelerators. In these machines, we take particles like electrons or protons and feed them energy again and again using electric fields, making them go faster and faster around a ring or down a straight line. If the old Newtonian picture were right, you could just keep adding speed more or less linearly. Instead, something different happens. As you pump more energy into an electron that is already moving at a high fraction of the speed of light, its speed increases, but by smaller and smaller amounts. The extra energy mostly goes into increasing its energy and its momentum, not into getting much closer to the speed of light. In older language, people said its relativistic mass is increasing. In modern language, we just say its energy is rising, and that affects how it responds to forces. The key point is that the speed approaches the speed of light as a limit, but never quite reaches it. The calculations you do with the relativistic energy-momentum relation match exactly what the machines see. You do not see a sudden jump past the limit. The limit pushes back harder and harder as you try to reach it. You can quantify this. The amount of extra energy needed to get a tiny extra step closer to the speed of light grows extremely fast as you approach the limit. To actually reach the speed of light, the required energy would blow up to infinity. That is not an engineering problem, that is a structural statement from the equations matched by the data. Acceleration experiments are like a direct conversation between your theory and reality, and they both say, this ceiling is solid. One more angle. Maybe the speed of light is not the same in all directions. Maybe the universe has some hidden preferred direction so that light going with it moves slightly faster than light going against it. That would mean the true limit is a little anisotropic, a little direction dependent. To test that, you build extremely stable optical setups, often with lasers bouncing between mirrors and cavities. You compare the frequency or phase of light traveling in different directions as Earth rotates and as it orbits the Sun. If there were a preferred direction in space, the component of your lab's motion along that direction would change with time. That would show up as tiny variations in the effective speed of light along your cavity, which would then show up as shifts in the measured frequency or interference pattern. The experiments are sensitive enough to see incredibly small changes. What they actually see are no such variations, within very strict bounds. Modern versions of this type of test have pushed the possible directional difference in the speed of light down to levels so small that for all practical purposes, the limit is isotropic, the same in every direction. So, add it up. Precision lab timing, same speed. High-energy photons across billions of light years, same speed. Neutrinos and light from a nearby galaxy-scale explosion, consistent with the same speed once you understand the astrophysics. Particle accelerators. Massive particles slam into the speed limit but never cross it, in perfect agreement with relativistic predictions. Directional tests, no sign of a preferred direction for the limit. This is why physicists treat C as a real ceiling and not just fancy language. Every time we design an experiment that could reveal a crack in that limit, the data comes back saying the same thing. If the rule fails, it does so beyond the reach of our current tools. And yet you've probably heard this line, light slows down in water, or light slows down in glass. On the surface, that sounds like a direct violation of everything we've just said. If C is the limit, how can light itself go slower in ordinary materials? And if it can go slower, why can't it also go faster somewhere else? How can light have a hard universal speed limit and at the same time slow down in something as boring as glass on your desk? That sounds like a contradiction. Either the speed limit is absolute, or materials are casually breaking it. This is where words get dangerous. When people say light slows down in glass, they are mixing two different ideas: the true speed of light in individual photons in empty space and the average progress of a wave moving through a crowd of charged particles. The true limit you've been hearing about is very specific. It is the speed of light in a vacuum with nothing in the way. That is where the constant shows up in the core equations of relativity and electromagnetism. Inside matter, air, water, glass, crystal, you are not dealing with free travel anymore. You have light trying to move through a dense jungle of electrons bound in atoms or in a solid structure. At that point, you are not only asking how fast does a photon move, but also how does it interact with the material as it goes? So here's the clearer version. Between interactions, when a photon is not being absorbed or scattered, it still moves at the vacuum speed limit. That part never changes. What changes is how long it spends stuck in interactions with the material. When you say light slows down in glass, you are really talking about the effective speed of a pulse, averaged over a lot of microscopic stop-start events. The speed limit is still intact. You are just watching a very messy commute. To see that more cleanly, think about a single photon entering a block of glass. At the boundary, it doesn't gently blend into the material, it either reflects, transmits, or gets absorbed and then re-emitted. If it goes in, the photon moves at the vacuum speed between atoms. Then it encounters an electron in the glass that can interact with that energy. The electron absorbs the photon. For a very short time, the energy is stored in that electron's motion or in a collective vibration. Then the system releases a photon again, usually in roughly the same direction as the original because of the way all those atoms respond together. From your large-scale point of view, that photon has done a stop-start pattern.
free flight at full speed, pause inside the material as energy in the electrons, free flight again, and so on. Each free segment is at the cosmic limit, but the pauses add delay. If you measure how long it takes a pulse of light to go from one side of the glass to the other and divide distance by time, you get a lower effective speed. That is what people casually call the speed of light in glass. Now add many photons and many atoms and treat them as a continuous wave instead of tracking each photon. In that wave, picture, the material responds to the oscillating electric field of the light. Electrons wiggle and sync, but with a slight lag. That lag changes the phase of the wave as it moves. When you work through the math, you get a new quantity, the refractive index of the material. In words, it's defined as the vacuum speed of light divided by the effective speed of light in that substance. So if the refractive index of water is about 1.3, that means light takes about 1.3 times longer to cross a certain thickness of water than to cross the same thickness of vacuum. For common glass, the index is around 1.5. You can measure this in two independent ways. One is by timing, send a short pulse through a known thickness and measure the delay. The other is by bending. When light passes from one medium to another, its path changes direction. The angle change depends on the ratio of the speeds in the two media, which is the same as the ratio of their refractive indices. Both timing and bending give you the same index. That tells you the slowdown is a real measurable effect of interactions with the material, not a change in the fundamental speed limit. This sets up a new kind of puzzle that sounds even more dangerous to relativity. In water or glass, the effective speed of light is lower than the vacuum value. But a charged particle, like an electron, moving through that water can still travel at a speed that is less than the vacuum limit, but greater than the slowed down light speed in the medium. In that case, the particle is, in a sense, outrunning the wavefront of light in that material. That sounds like faster than light, if you forget to specify which light you mean. When that happens, the particle produces a glow called Cherenkov radiation. You see it as a blue light in nuclear reactors or in certain detectors. The basic idea is similar to a sonic boom. When an object moves faster than the speed of sound in air, pressure waves pile up into a shock front. Here, when a charged particle moves faster than the effective light speed in the medium, the electromagnetic disturbances it creates cannot spread out smoothly ahead of it. They interfere in a way that produces a cone of radiation at a specific angle.
The key point: this particle is still slower than light in vacuum. It is not breaking the real speed limit. It is just moving faster than the slowed down wave in that medium. That is allowed and fully predicted by the same theory that sets the vacuum limit. So, Cherenkov radiation is not evidence against the speed limit. It is evidence that the medium's refractive index genuinely reduces the effective light speed there. Then there is an even stranger class of experiments where pulses of light in specially engineered materials appear to move faster than the vacuum speed, or even have parts of the wave packet that seem to exit a medium before they enter. At first glance, this sounds like a straight-up violation. The group velocity of the pulse is greater than the speed of light, or the peak of the pulse seems to jump ahead. This is where you have to separate different notions of speed. There's the phase velocity, which is how fast individual peaks of the wave pattern move. There is the group velocity, which is how fast the overall envelope of a wave packet moves. And there is the signal velocity, which is the speed at which new information can be transmitted. In weird materials with strong dispersion and absorption, the phase and group velocities can do bizarre things. They can be greater than the vacuum speed, less than it, or even negative in some definitions. But when you look at the very front edge of a signal, the first sudden change where new information actually appears, that front never outruns the vacuum speed limit. So no matter how fancy the wave tricks get, the part that matters for causality and for sending messages obeys the same rule. You cannot send a bit of information, a "this just changed now" signal, faster than light in vacuum. If some plotted velocity in a graph looks superluminal, it is always because that plotted quantity is not the actual signal speed. Once you define information speed carefully, relativity is safe. Put this all together and the story is tight. In vacuum, photons and any other massless excitations move at the universal limit. In matter, that limit still applies between interactions, but the stop-start process and the material's response slow the average progress. Refractive index quantifies that slowdown. Particles can outrun light in a medium, but not light in vacuum. And when they do, you get Cherenkov radiation, which the theory predicts. Exotic materials can make wave patterns that appear to move faster than the limit, but the first bit of actual information still respects the vacuum ceiling. So, light slows down in glass is not a counterexample to the speed limit. It is a reminder that you must be precise about what you are talking about, the motion of individual photons in empty space or the average motion of a wave through interacting matter. Once you separate those, the paradox disappears and the limit stands. Now, there is another challenge waiting. If spacetime sets this limit, and light always respects it in vacuum, what happens when spacetime itself is curved and distorted by gravity? Does light still move at the same local speed when it passes near massive objects, or can gravity cheat the rule by bending paths and stretching time? How can gravity twist the path of something with no mass and still never let it break the speed limit? In flat, empty spacetime, light follows straight lines at one fixed speed. When you add gravity in Einstein's picture, you do not add a new force that pulls on light, you change the stage itself. Mass and energy curve spacetime, and then matter and light follow the natural paths in that curved geometry. The rule is simple. Matter and energy tells spacetime how to curve, and curved spacetime tells matter and light how to move. The straightest possible paths in this curved spacetime are called geodesics. In flat space, a geodesic is a straight line on a diagram. In curved spacetime, that straightest path can look bent when you draw only the space part because both space and time are distorted together. Light always follows paths where the spacetime interval is zero, just like in special relativity. In a small enough region where curvature doesn't change much, light still moves at the same universal speed. Gravity doesn't change that local speed, it changes what counts as straight ahead. One of the cleanest tests of this idea is gravitational lensing. Take a massive cluster of galaxies. It curves spacetime around it. Put a more distant galaxy behind that cluster from our point of view. Light from the background galaxy travels through the curved region around the cluster. To us, that light seems to come from slightly different directions. On the sky, you see stretched arcs or multiple images of the same object. If you use general relativity to calculate how spacetime is curved by the cluster's mass and then trace light geodesics through that region, you get definite predictions for how much the light paths bend and how the images should look. Those calculations assume that along each tiny piece of the path, light still moves at the same local speed limit. The bending comes entirely from geometry. Observations of lensing, angles, shapes, even time delays between multiple images match those predictions. We even map dark matter by seeing how much lensing it causes. That tight agreement tells you gravity is steering light through curved spacetime without changing the basic speed rule. Timing tests show the same thing in a different way. Imagine sending a radio signal from Earth to a spacecraft or a planet on the far side of the sun and waiting for the echo. If space were perfectly flat, you could work out the round-trip time from the straight-line distance and the speed of light. In reality, when the radio waves pass near the sun, the signal comes back slightly later than that flat space estimate. This extra delay is called the shop road delay. The important point is that the radio waves are still locally moving at the universal speed along every tiny part of their path. The delay is not because light slows down near the sun. It's because the effective path through curved spacetime is longer in the time dimension than it would be in flat space. General relativity lets you calculate exactly how much added time you should see using the sun's mass and the geometry of the path. Measurements match those numbers. Once again, the limit stays in place. Only the route has changed. Near black holes, curvature gets so extreme that light can do things that sound impossible in ordinary space. Around a non-spinning black hole, there is a special radius called the photon sphere, where light can orbit in unstable circles, not just bending a little, but looping around the black hole. Intuitively, you might think light must slow down to stay in orbit, but that's not what the theory says. In the curved spacetime near the black hole, those circular paths are still geodesics for massless particles. Locally, a photon moving along one of these orbits still travels at the same universal speed. What has changed is the geometry.
Space near the black hole is warped so strongly that the straightest null path, the path with zero space-time interval, closes on itself in space. The orbit is unstable. A tiny inward nudge and the photon falls toward the horizon. A tiny outward nudge and it escapes. The existence and radius of this photon sphere come directly from the geometry, not from any change in light's own speed. Now look at how fast space-time itself carries information. When two neutron stars spiral together and merge, they send out gravitational waves, ripples in space-time, and also blast out light and high-energy radiation. In 2017, detectors picked up a gravitational wave signal from a neutron star collision, and telescopes saw light from the same event. The waves and the first gamma rays arrived with only a tiny time offset after traveling for over 100 million years. If gravitational waves moved significantly faster or slower than light in vacuum, that time difference would have been huge. Instead, the observed offset was small enough that you can put very strong limits on any difference between the speeds. Within our current sensitivity, gravitational waves and light share the same speed. That means the cosmic limit is not just about photons. It also controls how fast changes in space-time geometry itself can spread. So in general relativity, the picture is consistent. Locally, in any small region of space-time, light moves at one fixed speed. Gravity does not tweak that speed. It curves space-time, which changes which paths are available, how long they take, and how they look to us drawn on a flat diagram. Light and gravitational waves both move along the edges of the allowed causal structure, always at the same local rate. The weird bending and delays are all about the shape of the track, not the speed of what is racing along it. That leads to a firm conclusion. The speed limit is built into the geometry of space-time, even in the strongest gravitational fields we can observe. If you want to beat it, you are not just fighting a force. You are fighting the structure of space and time themselves. And yet, there is one more asymmetric twist. Massless things are forced to write exactly on that boundary, while anything with mass can only creep closer and closer from below, never reaching it. The next step is to look directly at that almost but never quite behavior and see how the same rules that lock photons to the limit also keep massive particles forever chasing and never catching the light. How hard do you have to push something with mass to make it actually catch light? Not just get close, actually match it. The honest answer is brutal. No finite push is enough. The closer you drive a massive particle toward light speed, the more the rules shift against you, until the idea of catching up stops being physically meaningful. Start with the basic pattern. In everyday life, if you double the energy of a moving car, you expect its speed to increase by a clear amount. Add more fuel, get more speed. That works well at low speeds. In relativity, the connection between energy and speed changes once you get to a significant fraction of light speed. You still pump in energy, but the payoff for extra speed gets smaller and smaller. If you plotted speed on the vertical axis and total energy on the horizontal axis, Newton's world would give you a smooth curve that keeps climbing. Relativity gives you a different shape. At low energy, the curve looks similar, no big surprise. But as the speed gets close to the universal limit, the curve bends and flattens out. You can keep sliding to the right, adding more and more energy, and the speed creeps closer to the limit, but it never actually touches it. It behaves like a curve that approaches a line without crossing it. That is what asymptote means here. A line the curve forever chases but never reaches. Physicists wrap this behavior into a single factor often called gamma. It is a number that tells you how strong relativistic effects are for a given speed. When your speed is much lower than the speed of light, gamma is almost exactly 1. Length contraction is tiny, time dilation is tiny, energy is basically the classic kinetic energy plus the rest energy. That is why Newtonian mechanics works so well for cars, planes, and even most rockets. As your speed gets higher, gamma starts to grow. At, say, half the speed of light, it's a bit above 1. At 90% of light speed, it's noticeably larger. As you push into 99%, 99.9%, and beyond, gamma doesn't just grow, it explodes. It increases so fast that near light speed, a small change in speed means a huge change in gamma. And here's the key. The total energy of a massive particle is its rest energy multiplied by this gamma factor. So as gamma shoots up, the energy you have to supply to squeeze out tiny gains in speed becomes enormous. If you imagine pushing a massive particle all the way to exactly light speed, gamma would have to become infinite. That means the total energy would have to become infinite as well. Infinite energy is not an engineering challenge. It's a signal that the situation is not physically allowed. The equations are telling you, trying to force a massive particle to have the same speed as light is trying to force the math into an impossible corner. This is not just algebra. We see it in machines we built. Look at the Large Hadron Collider at CERN. It accelerates protons to energies trillions of times higher than the energy those protons have sitting still. The speeds are so close to light speed that writing out all the nines is almost pointless. If you had a beam of light and a beam of these protons racing around the same 27-kilometer ring, lap after lap, the light would only pull ahead by a few meters per lap.
But that few meters never goes away. No matter how much more energy you pump into the protons, you never manage to make that gap exactly zero. You only make the gap smaller. The accelerators' magnets, the energy readouts, the collision patterns, all of it lines up with the relativistic formulas that say speed approaches the limit but never reaches it. You are seeing gamma going wild in hardware. Nature runs even more extreme tests than CERN. High-energy cosmic rays hit Earth from deep space with energy so huge that a single particle can carry as much energy as a hard-hit tennis ball. That is absurd for something subatomic. If any massive particle had a chance to break the speed limit, you would expect it here. But when you work out the actual speeds from those energies using the relativistic energy-momentum relation, the story repeats. The speeds are unbelievably close to light speed, but still lower. The difference from c is tiny, but it is not zero. This matters because it tells you the pattern is not a fluke of human technology. Across natural and artificial accelerators, the same rule holds. As you add energy to a massive particle, you mostly increase gamma, not the actual speed. The velocity curve flattens out. The limit is hard. Now tie this back to photons and other massless particles. They obey the same overall energy-momentum relation, but with a crucial simplification. Their rest mass is exactly zero. In that case, the piece of the relation that depends on mass drops out, and you are left with a direct link between energy and momentum. From that, when you interpret what speed those values correspond to, you do not get any speed is fine. You get exactly one consistent solution. The speed must equal the universal limit. If you tried to have a massless particle move slower than that limit, its energy and momentum would not fit the relation that everything else obeys. If you tried to make it move faster, you are again outside the allowed region. The same mathematics that forces massive particles to forever chase the limit from below forces massless particles to live exactly on the limit. You do not get to modify one side of that story without breaking the other. So the structure is tightly locked. Massive stuff, always below. Asymptotically approaching but never catching light. Massless stuff, always on, never below, never above. The speed limit is not an add-on. It is built into the way energy, momentum, and mass fit together in relativity. Change the limit and you wreck the match between theory and accelerator data, between theory and cosmic rays, between theory and causality arguments. You cannot pull on one thread without tearing the whole fabric. But all of this has treated particles as if they were little beads with mass or no mass sliding through space-time. Modern physics goes deeper and says that even those particles are not fundamental. They're excitations of fields that fill space. And in that language, the question becomes sharper. Why does the field that we call electromagnetic insist that its excitations, photons, are massless so that they are nailed to the speed limit? What in the rules of the field itself blocks you from giving the photon even a tiny mass and letting it slip off that edge? Why does the universe feel so strict about the photon's speed that it builds the rule right into the deepest layer of reality? Up to now, we've treated photons like tiny bullets with no mass that just happen to move at the speed limit.
Quantum field theory flips that picture. In this framework, the basic ingredients aren't particles at all. They're fields that fill all of space, even where there seems to be nothing. In this view, every particle type you know is just a particular kind of vibration in its corresponding field. Electrons are excitations of the electron field. Quarks are excitations of quark fields. And the photon is the smallest possible ripple of the electromagnetic field. You don't have a photon first and then decide it has an associated field. You have the field first. Quantizing that field produces photons as its energy packets. That already changes how you think about the speed limit. The question stops being, why does this little particle move at that speed? And becomes, why does this field only support ripples that move at that speed in vacuum? The answer is in the rules that the electromagnetic field is forced to follow. Here's where a crucial idea enters: symmetry. The electromagnetic field has a very specific internal symmetry. In simple terms, you can change the phase of the charged matter fields, basically twist their internal angle, differently at different points in space and time, and as long as you adjust the electromagnetic field in just the right way, all the observable physics stays the same. That requirement is called a gauge symmetry. You do not impose the symmetry just for fun. Once you demand that the laws of physics look the same under these local phase changes, you are almost forced to introduce something like the electromagnetic field, and its interactions with charged particles are tightly constrained. The structure of Maxwell's equations and the existence of a massless photon fall out of that symmetry rule. Now, here's the key. If you try to add a simple mass term for the photon into those equations, you would break that gauge symmetry. The beautiful freedom to shift phases locally while keeping the physics unchanged would be lost. The theory would predict different things for experiments that, in reality, give the same result. Since we see electromagnetic gauge symmetry working extremely well in experiments, from atomic spectra to accelerator collisions, you are pushed to the conclusion that the photon's mass must be exactly zero in the theory we trust, or so tiny that any breaking of the symmetry is far below what we can detect. That leads to an obvious next question, which is, how tiny is tiny? If the photon had a minuscule mass, the symmetry would be approximate, not exact, and its effects would show up in how electric and magnetic fields behave over very large distances. For example, a photon with mass would cause electric fields from a point charge to fall off a little faster than the usual inverse square law at great distances. Large-scale magnetic fields in galaxies and clusters would also behave differently if the photon were even a little bit heavy.
Astronomers and experimentalists go hunting for these deviations. They study magnetic fields stretched across galaxies. They look at how the solar wind and planetary magnetic fields behave. They probe whether static electric fields really extend as far and as cleanly as Maxwell's massless theory says. So far, everything matches the massless predictions to incredible precision. The results only allow the photon's mass, if it is not exactly zero, to be at most an insanely small value. Saying tiny here means so small that for any experiment you can imagine, the photon behaves exactly like a massless particle, and the speed limit story does not change at all. So the field theory backbone is, gauge symmetry wants the photon massless, and observations agree. A massless excitation of the electromagnetic field is forced to move at the universal speed limit in vacuum. If you break that at a fundamental level, you have to explain why all these symmetry tests and large-scale yield observations still look exactly like the massless case. Then there's the worry. Quantum mechanics allows probabilities to spread out and interfere. So could it also let influences leak outside the light cone a little and sneak around the speed limit in some fuzzy way? Quantum field theory answers that with another strict rule. When you write down how disturbances in a field propagate from one event to another, the mathematical objects that describe this, the propagators and commutators, are built so that cause and effect influence is strongly suppressed outside the light cone. In practical terms, this means if you take two events that are separated in space-time in a way that puts them outside each other's light cones, the field operators at those events either commute or have effects arranged so that no measurement in one region can be used to send a controllable signal to the other. There can be non-zero mathematical amplitudes floating around, but they do not translate into, I do something here now and you see a reliable effect there earlier than any light signal. The structure of the theory is designed to keep usable information trapped inside or on the light cones, even in the quantum regime. This connects directly to the strange experiments you hear about. In a double-slit setup, single photons produce interference patterns. In entanglement tests, measurements on one photon seem to be linked to outcomes on another, far away, in a way that does not fit classical expectations. It is tempting to look at that and say, there, that must be faster than light communication. But when people do these experiments carefully, they find something subtle. Yes, the correlations are real and cannot be explained by simple local hidden variables, but you cannot use them to send a controlled message faster than light. You cannot choose one outcome here that forces a chosen outcome there and thus transmit a bit of information outside the light cone. The statistics obey the no signaling rule. Every time when you track what is actually observable and controllable, the speed limit is safe. So photons are absolutely weird in the quantum sense. They interfere with themselves, they come in discrete packets, they show polarization behavior that needs quantum spin, and they participate in non-classical correlations. But at the same time, they obey all the relativistic restrictions you have built up so far. They move at the universal limit in vacuum because their field is constrained to be massless by gauge symmetry. Their propagation is tied to the light cone by the core structure of quantum field theory. Their quantum tricks do not open up a channel for faster-than-light signaling. The picture that emerges is tight. From the deepest theory we have, up through cosmic magnetic fields, down to lab experiments with lasers and detectors, the photon behaves like a massless excitation that rides the edge of the causal structure and never leaves it. That means the speed limit is not just a classical rule or a geometric rule. It is built into the quantum description itself. But there is still one apparent escape route that people love to bring up: the expansion of the universe. You hear that distant galaxies are receding faster than light, or that during inflation, space itself expanded faster than light could cross it. If locally nothing can outrun light, how can entire galaxies end up separating from us faster than light would cover the distance? Does expanding space actually slip around the limit? How can distant galaxies be moving away faster than light, and yet you're told nothing can outrun light without tearing causality apart? On the surface, that sounds like cosmology is quietly breaking the exact rule relativity drilled into you. The fix is simple, but very non-intuitive. Those galaxies are not racing through space past some speed limit sign. The space between you and them is stretching, and the way we describe that stretching makes the separation grow in a way that can be faster than light without any local law being violated. In everyday thinking, velocity means how fast one thing moves through space past another. In expanding universe thinking, you're often talking about something else: how fast the distance between 2 points grows because the scale of space itself is changing. In general relativity, that changing scale is baked into the solution we use for the universe on large scales. So when you read that a very distant galaxy is receding from us faster than light, the statement is about the rate at which the distance between us increases in those cosmological coordinates, not about that galaxy racing through a static medium at forbidden speed. So how do we quantify that receding in a way that doesn't just sound like word games? Observations of galaxies show a clear pattern. Their light is redshifted, and the redshift grows with distance. The simplest summary is this: the farther away a galaxy is, on large scales, where local motions average out, the faster it appears to be receding from us. If you double the distance, the recession rate roughly doubles. This is the content of what's usually called Hubble's law, but we can say it without equations. Apparent recession speed is roughly proportional to distance. Now, push that pattern out. If at some particular distance, the apparent recession speed is, say, half the speed of light, then at twice that distance, it is around the speed of light, and at 3 times that distance, it is around 1.5 times the speed of light, and so on. At some large enough distance, this recession speed exceeds the speed of light. That sounds like a violation until you remember what that speed is measuring. It is not a velocity you would plug into the special relativity formula for time dilation between 2 ships in the same region. It is the rate at which the scale factor of the universe is pulling 2 far-separated, mostly stationary galaxies apart. Locally, each galaxy can say, I'm basically at rest with respect to the cosmic background, and in each small region, special relativity still holds, and nothing moves faster than light through that region. This shows up clearly in the story of the cosmic microwave background, the afterglow of the Big Bang. Those photons have been traveling for about 13.8 billion years before hitting your detectors. If space were static, you might expect the places that emitted that light to be around 13.8 billion light-years away now. But in the coordinate system cosmologists use, those regions are much farther, tens of billions of light-years away, because space has been stretching the whole time the photons were on the move. Here's the important detail. At every moment along the photon's journey, if you zoom into a small enough patch of space around it, the photon is moving at the usual speed limit relative to nearby matter. Locally, nothing weird is happening, but globally, the distance between here and the original emission region keeps increasing because the scale of the universe is changing. The photons are like runners who keep moving forward at the same pace while the track beneath them is slowly being stretched. The stretching increases the gap between starting line and finish line in a way that does not come from the runners breaking their own speed. Now crank this idea to an extreme: inflation. According to our best models, in the very early universe, there was a phase where the expansion rate was not just steady, it was exponential. That means the distance between two fixed points in the coordinate system doubled over a very short, constant time interval, then doubled again and again. During that phase, the separation between points grew so fast that no light signal could hope to cross from one to the other in time. Distances were increasing much faster than light could cover them. The trap would be to say, then space was expanding faster than light, so the speed limit is broken. But in general relativity, the rule is not the size of the universe can't change faster than light. The rule is that in any small neighborhood where space-time looks nearly flat, no object can move through that neighborhood faster than light, and no signal can overtake a light beam as they travel side by side. During inflation, that local rule still holds. Local observers still find that light moves at the universal limit in their labs. What is changing is the mapping from this coordinate now to that coordinate later on the global scale. So what is the correct way to phrase the limit once you understand expansion? It's more subtle than nothing can go faster than light, period. The refined statement is nothing can locally outrun light in spacetime. You cannot sit in your spaceship, shine a beam, and then arrange for your ship to pass that beam and beat it to a destination that is nearby in the sense of local geometry. You cannot send a signal that arrives outside the future light cone of its emission event. Global stretching of the entire metric, which is the mathematical object that defines distances and times in general relativity, is a different kind of thing. It changes what distance means between widely separated points as time goes on. That can make recession speeds larger than the speed of light when you define them as change in distance per unit cosmic time. But those are not the speeds that enter the local no faster than light rule of special relativity. So you end up with a clear division. Locally, space-time looks approximately flat. The speed of light is a hard ceiling, and all the arguments about energy, momentum, and causality apply. Globally, the geometry itself can evolve in ways that make coordinate distances grow at effective rates above the limit without any object ever finding itself in a frame where it is literally crossing its local light cone. That closes one of the most popular supposed loopholes. Galaxies receding faster than light and inflation expanding space faster than light can cross it do not stab relativity in the back. They are examples of relativity being applied correctly on large scales. The speed limit is a rule about local motion and causal structure, not a ban on the universe's overall size changing quickly. But if expansion can play tricks with the meaning of speed, you might wonder, what if you went further and really allowed a signal to move faster than light in the local sense? Not just coordinate games, but true faster-than-light messaging between nearby points. The geometry and the quantum rules wouldn't just complain a little, they would let you build machines that send information into their own past. The next step is to follow that idea to its ugly end and see why breaking the limit doesn't just make things a bit weird, it blows up the basic idea of cause and effect. How badly does reality glitch if you allowed a truly faster-than-light signal? Not subtle correction to an equation bad, more like send a message and get the reply before you send the message.
To see why, you have to accept one key result from relativity that already clashes with intuition. Different observers do not agree on what counts as at the same time. Start there. In relativity, simultaneity is not absolute. Take two events that are separated in space. Maybe a flash goes off at one end of a long spaceship and another flash at the other end. If you sit at rest with respect to the ship and you place synchronized clocks at both ends, you can say whether those two flashes were simultaneous according to your clocks. Now, let someone else fly past the ship at high speed. They carry their own synchronized clocks in their frame. When they analyze the same two flashes, they do not get the same answer about which happened first or whether they were truly at the same time. This is not just a story. It drops directly out of the way space and time coordinates transform between moving frames in special relativity. That transformation has been checked over and over in muon lifetime measurements, in fast particle experiments, in clock comparisons between planes and ground, in GPS satellites. Moving clocks really do tick at different rates. Moving observers really do slice spacetime into now surfaces differently. There is no single global now everyone agrees on. On its own, that is weird but manageable. As long as signals are limited by the speed of light, everyone will still agree on the order of causally linked events. If event A can affect event B by a light signal or anything slower, then all observers will say A happens before B. You can disagree about simultaneity for space-like separated events that cannot influence each other, and the universe does not care. The trouble starts when you introduce a signal that is faster than the speed of light. Set up a simple scenario. You are floating in space with a fast-moving friend passing by in a spaceship. You both have devices that can send signals instantaneously according to your own rest frame. That means press a button, and in your frame, the signal appears somewhere else with no delay, even if that somewhere is far away. That is already a violation of the light speed rule, but suppose you allow it for now. You and your friend are moving relative to each other, so each of you has a different definition of which events are simultaneous. Now do the following. In your frame, at some time you label as 0, you send an instantaneous signal to your friend. In your coordinates, the signal appears at your friend's location at the same moment, time 0. Your friend receives it and, by their own rules, waits a short proper time, maybe a few microseconds by their clock, and then sends an instantaneous reply back to you. In your friend's frame, that reply appears back at your location at the same moment they press send. Because the two of you disagree on simultaneity, when you transform the sequence back into your own frame, something ugly happens. The event friend sends reply and the event you receive reply line up differently in your time coordinate than they do in your friend's. With the right relative speed and the right orientations, you can arrange things so that in your frame, the reply arrives before the time you sent the original message. From your point of view, your friend has answered a question you have not asked yet. You can push this further. By chaining together cleverly chosen faster-than-light exchanges between people in different states of motion, you can build a closed loop in time. Start at event A. You decide whether to send a message based on some condition. The message goes out faster than light to someone else, who then sends another faster-than-light message in a different frame. After going through a few such steps, the last signal in the sequence arrives back to you at event B. With the right setup, event B can lie in your own past light cone relative to event A. In your coordinates, you receive information before you made the decision that was supposed to trigger that information. You could receive a warning that says, "Do not press the button." If you obey, you never send the initial message. If you never send it, the chain of responses never starts. If the chain never starts, the warning never returns to you. Then you have no reason not to press the button. Pressing it starts the chain, which sends back the warning that stops you, and you are stuck in a logical loop. These are not just storybook paradoxes. They are direct consequences of two ingredients: relativity's relativity of simultaneity and the existence of any signal that can outrun light locally. Together, they allow you to connect events in spacetime in ways that make cause and effect change places depending on the frame. The moment you permit a local faster-than-light influence, you lose the guarantee that causes always precede their effects in every allowed frame. Our current physical theories are built to avoid this kind of inconsistency. Classical mechanics conserves energy and momentum and assumes a well-defined state at each time that determines the future. Thermodynamics defines an arrow of time through increasing entropy, but that arrow still assumes that causes come before their macroscopic effects. Quantum mechanics encodes evolution through a rule that takes one state to another in a way that preserves probabilities and correlations. All of those frameworks lean on the idea that you can order events in a way that does not generate contradictions. If you allow machines that send usable information into their own past, you can attack those foundations. You can imagine arrangements where, depending on what choice is made, the very inputs to the situation change. You can produce histories that have no consistent global description. In that kind of world, state at time t stops having a clear meaning because the future can reach back and modify the conditions that were supposed to produce it. Relativity avoids this disaster by tying causality to the light cone. Inside or on the cone, events can be causally related. Outside the cone, they cannot. That structure, plus the requirement that all physical laws have the same form in all inertial frames, naturally leads to a maximum local signal speed. If you try to exceed that speed, you automatically gain the ability to build these time loops. There is no halfway house where you get a little bit of faster-than-light signaling without also opening the door to backwards in time influence in some frame. So the speed limit is not a random preference. It is not mainly about the engineering difficulty of pushing rockets. It's a guardrail on logical consistency. Keep every physical influence at or below the speed of light locally, and all observers will agree on the order of cause and effect for events that actually influence each other. Break that rule, and you can construct machines that destroy that agreement and produce paradoxes that have no stable resolution. In that sense, the speed of light is acting as a kind of bodyguard for logic. It's the maximum slope that causal lines are allowed to have in spacetime diagrams. It keeps the future from leaking into the past in ways that would let you kill your own signal before you send it. Every time an experiment checks the limit and finds no violation, it's not just confirming an equation, it's confirming that the universe refuses to let you build a time paradox device. Of course, hearing all this, the next thought is obvious. People still talk about warp drives and wormholes as ways around the limit. These ideas claim to let you get to distant places effectively faster than light without, supposedly, sending a signal through normal space faster than light. So the question becomes, do those concepts really avoid the causality traps, or do they just move the problem into the geometry and run into even harsher conditions there?
How close does science fiction actually get to beating the speed limit if you use spacetime itself as the engine? General relativity does allow some very strange exact solutions. On paper, you can bend spacetime into shapes that let you go from A to B effectively faster than a light beam that travels through normal space. The key word is effectively. In these ideas, you never sit in a ship and blast through local space faster than light. You sit inside a region of curved spacetime that moves in a special way. Take the classic example, a warp drive metric. In one family of solutions, spacetime is arranged into a kind of bubble. In front of the bubble, distances contract. Behind the bubble, distances expand. The bubble itself moves through the larger universe. Inside the bubble, you float comfortably. Relative to your local surroundings, you are not going faster than light. All the local physics is normal. Light cones, speed limit, everything. But relative to some distant star, the bubble center can move so that the separation between you and the star shrinks faster than a light beam in normal flat space could manage. On paper, this sounds like a neat trick. You do not push the ship through space faster than light, you drag the region of spacetime containing the ship. The problem shows up when you ask, what kind of stress energy is required to curve spacetime in exactly this way? When people compute this, they find that the stress energy needed for these warp bubbles is not ordinary positive energy density like you get from dust, gas, or radiation. It includes regions where the energy density, as seen by some observers, is negative. Negative energy density means matter that gravitates in the opposite way to normal matter. Instead of pulling things in, it would push them away, at least in some directions or for some observers. Normal classical matter does not do this. Quantum field theory does allow situations where, in a small region and for a short time, you can get negative energy densities relative to some baseline. But these are tiny, transient effects, like brief dips created by the Casimir effect or in squeeze quantum states. Not large, long-lived blocks of negative energy stuff you can mine and shape. For a warp bubble big enough to carry a ship, the amount of exotic, negative energy like stress energy needed is enormous. Early estimates were absurdly huge, more than the mass energy of entire stars. Later work trimmed some of those numbers, but the basic requirement remains. You need matter or field configurations that we do not know how to produce, control, or even exist in the required form. And if you try to weaken the requirement, the bubble tends to either collapse or become useless. Wormholes hit the same wall from another direction. The equations of general relativity do allow solutions that look like tunnels connecting distant regions of spacetime. In simple diagrams, you might see two distant mouths and a throat connecting them. If such a wormhole were traversable, meaning you could go in one mouth, travel through, and come out the other without being crushed, you could, in principle, go from one place to another faster than a light beam traveling through normal space between those places. The trouble is not writing down a metric with that shape. The trouble is what the stress energy has to look like to support it. For a stable, traversable wormhole throat that does not pinch off as soon as you try to pass through, the energy conditions of general relativity are violated. In plain terms, you again need negative energy density in some region to hold the throat open and keep tidal forces under control. Positive energy alone makes throats collapse or form horizons that trap anything trying to escape. Quantum field theory does show that negative energy densities can occur, but it also pushes back. There are results called quantum inequality bounds that say you can't just have arbitrarily large negative energy in an arbitrarily big region for an arbitrarily long time. The more negative energy you try to pile up, the shorter the time it can exist or the smaller the region you can pack it into. These bounds are not just loose suggestions. They come out of the structure of quantum fields in curved spacetime. When you apply those kinds of restrictions to the stress energy needed for warp bubbles or traversable wormholes, the picture gets grim. To get a geometry that lets you travel meaningful macroscopic distances faster than a light beam in normal flat space, you need negative energy arranged in ways that seem incompatible with those quantum limits, or you need to violate assumptions that are deeply tied to the stability of the vacuum itself. That doesn't prove warp drives and traversable wormholes are absolutely impossible in all logically consistent theories, but it pushes them far outside anything that looks like realistic physics as we understand it. There is another issue sitting in the background. Many space-time geometries that allow effective faster-than-light travel or shortcuts also allow, with the bit of motion of the mouths or the bubble, the construction of closed time-like curves, paths that loop back in time for some observers. In other words, the same geometries that tempt you with go there faster than light also tempt you with send signals into your own past. You're back in the territory of causality paradoxes and self-contradicting histories. That's a strong hint that the full quantum theory of gravity, once we have it, may enforce extra rules that quietly kill off these pathological configurations. Even if you ignore the causality issue and focus just on local behavior, one thing is consistent across all these speculative constructions. Nobody actually sits in a rocket and locally moves faster than light. Inside the warp bubble, inside the wormhole throat, local speeds relative to the immediate spacetime are always at or below the usual limit. The cheat is entirely in how the geometry is arranged across large regions. You're not really breaking the local speed rule, you're trying to exploit global curvature to change what path between A and B means.
So the situation is this. The equations of general relativity, taken in isolation and pushed into highly exotic regimes, admit solutions that look like shortcuts or faster-than-light detours. But those solutions demand matter and energy in forms that clash with what quantum field theory allows on large scales and for long durations. They often drag in time travel problems as an unwanted side effect. And in every version, local motion still respects the same speed limit. That leaves you with a clear message. Even the wildest loopholes in the classical equations seem to close when you add the quantum side and the demand for causal consistency. If there is a safe, physical way to get effective faster-than-light travel, it will require new physics that somehow evades all these constraints without destroying everything else we know works. Right now, that looks extremely unlikely. But extremely unlikely is not the same as we stop checking. Physicists don't just assume the limit is unbreakable and walk away. They design experiments to look for even tiny violations of the rules that enforce the speed limit. Tiny failures of Lorentz symmetry, tiny directional preferences, tiny energy-dependent changes in speed. If C ever cracks, it'll probably crack first in those subtle ways, not with a starship jumping to hyperspace. So the next question is, what do the most precise tests of these symmetries actually say, and how hard have we already pushed on the cosmic speed limit to see if it ever blinks? How do you know physicists haven't just gotten comfortable with the speed of light and stopped checking it? The honest answer is they keep attacking it. The core symmetry behind relativity has a name: Lorentz symmetry. It says the laws of physics look the same for all observers moving at constant speeds relative to each other, and that the speed of light in vacuum is the same in all directions and at all energies. That symmetry is the backbone of special relativity. Some ideas for quantum gravity, the still unknown theory that should unite quantum mechanics with general relativity, suggest Lorentz symmetry might only be approximate. Maybe at extreme energies or on ultra-small scales, the symmetry is slightly broken. If that were true, the maximum signal speed might not be exactly the same in all directions or at all energies. That's a huge claim, so people look for even tiny cracks. The strategy is simple. You search for situations where even a tiny change in the speed of light would pile up into something measurable. One of the cleanest tests comes from gamma-ray bursts and similar violent events. A distant explosion in a galaxy sends out photons across a wide range of energies almost at the same time. These photons then travel for billions of years to reach us. If higher energy photons traveled even a little faster or slower than lower energy photons in vacuum, the difference in arrival times would grow during that huge journey. A tiny fractional change in speed could become seconds or minutes of delay between different energy bands. Astronomers record the light curves of these bursts in different energy ranges and look for consistent patterns. Do the highest energy photons arrive systematically earlier or later than the low energy ones? If Lorentz symmetry were slightly broken in certain ways, you'd expect a clear trend. So far, after many events and careful analysis, the result is boring in the best sense again. Once you account for how the source itself emits photons, there is no robust repeating delay pattern that points to an energy-dependent speed of light in vacuum. Any deviation must be below the current sensitivity. That pushes possible symmetry-breaking effects to extremely tiny levels. Another powerful test uses cosmic rays, the ultra-high energy particles that slam into Earth from space. There's a well-understood process where extremely energetic cosmic rays interact with the photons of the cosmic microwave background, the leftover radiation from the Big Bang. Those interactions should cause very energetic protons to lose energy over long distances, producing a cutoff in the spectrum. Above a certain energy, you expect to see far fewer particles arriving. This predicted suppression shows up in data. The observed spectrum of ultra-high energy cosmic rays drops off around the energy you expect if you assume Lorentz symmetry holds and the speed of light is energy independent. If the maximum speed for different particles depended strongly on energy in the wrong way, those interaction thresholds would shift. The cutoff would move or blur in ways we don't see. So the fact that the cosmic ray spectrum behaves roughly as expected is indirect but strong support that relativity is still working even at ridiculous energies. Back on Earth, you can do another kind of test. Look for any direction in which light behaves differently. If space had a preferred direction, or if the speed of light were slightly higher along one axis and slightly lower along another, you could pick it up by carefully rotating an experiment over time. Modern versions of the Michelson-Morley idea do exactly this, but with much better technology. Ultra-stable lasers are bounced between mirrors in high-quality cavities. The frequencies at which these cavities resonate depend on the effective speed of light along the cavity. As Earth rotates and orbits the Sun, the orientation and speed of the lab change relative to any hypothetical preferred frame. If the speed of light depended on direction or on Earth's motion through some hidden background, the resonant frequencies would drift in a signal pattern as the apparatus turns with the planet. Experiments monitor these frequencies with insane precision. The result? No such pattern, within very tight error bars. Any directional dependence in the speed of light must be smaller than those limits, which are already extremely small fractions of the speed itself. There are also collider and atomic experiments that look for Lorentz-violating effects in particle interactions, energy levels, and decay rates. You can build a general framework where you add all possible small terms that would break Lorentz symmetry in known equations, and then you ask, how big could those terms be without contradicting existing measurements? Over the years, many of those possible terms have been squeezed down to limits so tiny that for all practical purposes, the symmetry might as well be exact. Put all of this together and you get a clear picture. Across enormous distances and times, gamma-ray bursts and cosmic rays, across extreme energies, particles far beyond what our accelerators can reach, across precise, quiet lab setups, lasers in cavities, clocks on satellites, measurements of atomic transitions. Every time you give the speed limit a chance to wobble, it refuses. If there is any energy dependence, any directional bias, any tiny twist in Lorentz symmetry, it is hiding below the thresholds of experiments that are already incredibly sensitive. So when physicists say the speed of light in vacuum is the same for everyone, everywhere, they are not just leaning on Einstein's authority or on pretty diagrams of light cones. They are leaning on decades of people trying to break that statement and failing. If the cosmic speed limit does break down, it will probably be in some extreme regime that we have not yet probed. Energies near the Planck scale or distances and times near the Big Bang where quantum gravity effects dominate. For now, every accessible test tells you the same thing. C stands untouched. That pushes you to ask a deeper question. If this speed really is that universal and that robust, is it just a number with units attached, like 300,000 kilometers per second? Or is it something more fundamental? Is c just a speed that light happens to have, or is it the built-in conversion factor that links space and time into one structure, part of the hidden skeleton of the laws themselves? Is the speed of light just a random trivia number, or is it wired so deep into the rules of reality that you can't even talk about space and time without it? When theorists really want to see the bones of the equations, they don't write 300,000 kilometers per second anywhere. They literally set the speed of light equal to 1. Not approximately 1, exactly 1, by choice of units. Here's what that does. Normally you measure distance in meters and time in seconds. They're different units, so you have to carry this big meters per second factor around to convert between them. But if you pick your unit so that the speed of light is exactly 1 unit of distance per 1 unit of time, then a unit of time literally is a unit of distance, the distance light covers in that unit of time. You might say 1 time unit equals the distance light covers in that time unit. In those units, if an object moves at half the speed of light, its speed is literally 0.5. No kilometers, no seconds, just a pure number. Doing this doesn't change physics, it just changes how you write the numbers. But the fact that this trick is so useful already tells you something important. The speed of light is not just how fast photons go, it's the built-in conversion rule between spatial separation and time separation. It lets you treat space and time in the same unit system, which is exactly what relativity wants you to do.
Think of it like an exchange rate. You have space in meters and time in seconds, and c tells you how many meters of light travel you get per second. Roughly 300,000 kilometers per second means, in 1 second, light covers about 300,000 kilometers of distance in vacuum. Flip that around and you can say 1 kilometer of distance corresponds to a certain tiny slice of time for a light signal. In the usual classroom view, this is just a curiosity.
In the relativistic view, it's central. If you want to compare how far apart two events are in a way that respects the structure of spacetime, you can't just look at the space gap or the time gap separately. You have to combine them. And to combine them, you must first put them in the same units. That's where the speed of light comes in. Multiply a time difference by the speed of light, and now it's in distance units. Or divide a distance by the speed of light, and now it's in time units. Relativity uses that to define the space-time interval between two events. In words, you take the time difference, convert it into an equivalent distance by multiplying by the speed of light, square that, and subtract the square of the actual spatial separation. That combined quantity, the interval, has a special property. All observers, no matter how they move, agree on its value. They disagree on the raw time and raw distance, but they agree on this specific combination. This is the deeper distance in spacetime, and c is baked right into how you compute it. Different types of separations between events fall into categories based on this interval. If the time term is big enough that the interval comes out positive when you do that time part minus space part combination, the events are time-like separated. A signal moving slower than light can get from one to the other. If the time and space parts balance perfectly so that the interval is zero, that's light-like separation. Only a signal moving exactly at the speed of light can connect them. If the space part is too big and the interval comes out negative, that's space-like. No causal signal, even at light speed, can connect them. The whole classification depends on the speed of light as the conversion factor between the time and space parts. So asking, what is c really, is a bit like asking, what is the conversion between meters and seconds that makes this special invariant distance formula work? Change that conversion factor, and you change the shape of light cones, the classification of separations, and what counts as reachable in a given time. In that sense, c is part of the skeleton of space-time geometry, not just a label on photon speed. Then comes the speculative question. Could another universe have a different value of c? You can imagine a world where, when you measure in our familiar meters and seconds, the speed of light comes out to a different number. At first, that sounds like a big physical change. Light is slower or faster. But you have to be careful. The raw value you write down depends on the units you choose. If you switch to units where c equals 1, you erase that difference by definition. So saying c is larger in that universe only becomes meaningful if you compare it to something else that also has units, like the gravitational constant, Planck's constant, or characteristic particle masses. What really matters physically are the dimensionless ratios, pure numbers with no units attached. For example, how strong electromagnetism is compared to the force that binds nuclei, or how the electron mass compares to some natural energy scale. You can build such pure numbers by combining constants like the electric charge, Planck's constant, the vacuum permittivity, and the speed of light in a way that cancels units. One famous result of that game is the fine structure constant, usually written as approximately 1 divided by 137. It measures the strength of electromagnetic interactions in a dimensionless way. That constant includes c in its definition when you write it in common units. So if you change c while holding some other constants fixed, you would change the value of that dimensionless coupling. That in turn would change real physics, atomic sizes, spectrum lines, chemical behavior, how stars burn. Different values of these pure numbers mean different types of structures can or cannot form. Some arguments suggest that only a fairly narrow range of these dimensionless constants allows long-lived stars, complex chemistry, and stable structures like planets. In that sense, c matters not because of its units, but because it enters into these deeper, unit-free combinations. Many physicists think that at the most fundamental level, only those dimensionless constants are really fundamental. You can always choose units to make c, or Planck's constant, or the gravitational constant equal to 1 in your equations. But you cannot choose units to erase a number like 1 over 137. That pure ratio is an input you can't get rid of by rescaling. And c is part of how you build that number in the first place. So the modern view is layered. On one level, c is just the speed you measure for light in vacuum, about 300,000 kilometers per second. On the next level, it is the conversion factor that fuses space and time into spacetime and defines the invariant interval. On a deeper level, it is one of the constants that appear inside the truly fundamental dimensionless numbers that control how strong forces are and how structures form. That is why, when physicists write equations in natural units with c set to 1, they are not downgrading its importance. They are doing the opposite. They are acknowledging that space and time are so tightly linked by this constant that it makes more sense to measure them in the same kind of unit. The speed limit becomes 1 not because it stopped mattering, but because it is so central that it becomes the baseline. Which brings you back to the original question that kicked this all off. If c is that deep a part of space-time's skeleton, and photons are forced to ride that skeleton at its maximum rate, what does that really mean for the original paradox? A massless particle with a limited speed. You've now seen the pieces, from energy and momentum, from fields and geometry, from causality and experiments. The last step is to put them all together into one clear answer to the question, light has no rest mass, so why isn't its speed infinite?
So after all this, what is the real answer? You started with a simple, annoying question. If light has no rest mass, why doesn't it just move infinitely fast? Why is there a limit at all? The key thing you've seen is that this is not really a story about light being held back. It's a story about what our space-time even allows as a possible cause and effect connection. The speed we call the speed of light in vacuum is not mainly a property of photons. It is the maximum rate at which any influence can move from one event to another. It's the steepest slope any causal line is allowed to have in space-time. Photons just happen to be the simplest things that ride that boundary cleanly. They don't slow down in vacuum because they can't. They also can't speed up because that would mean trying to send causal influence outside the allowed region of spacetime, outside the light cone. You can see this directly in the energy-momentum rule. When you write the full relationship between energy, momentum, and mass in words, it says the square of the total energy divided by the square of the speed of light equals the sum of two pieces, one that depends on the square of the mass times the square of the speed of light, and one that depends on the square of the momentum. That's the master constraint. It tells you which combinations of energy, momentum, and mass are allowed for any particle. If you now plug in mass equals 0, you do not get energy can be anything, speed can be anything. The mass term disappears, and you're left with a direct link between energy and momentum, and that link corresponds to exactly one speed, the universal limit. A massless particle can change direction, it can change energy and momentum, but if it exists as that kind of excitation at all, its speed must be the same fixed value in vacuum. Massless does not mean no rules. Massless means forced onto the boundary. Massive particles are trapped on the inside of that boundary by the same rule. As you pour more and more energy into them, their momentum grows, their gamma factor explodes, but their speed only crawls closer to the limit. To actually reach the same speed as a photon, a massive particle would need infinite energy, because the mass term in that master relation never goes away. That's why accelerators see speeds that get closer and closer to light speed but never reach it. That's why cosmic rays with insane energies still come in just under the limit. The rule that locks photons on the edge is the same rule that keeps massive stuff from ever catching them. Then you wrap that into spacetime geometry. The speed limit defines light cones.
Inside your future cone are events you can, in principle, influence. Inside your past cone are events that can, in principle, influence you. On the surface of those cones are paths that only massless things can follow. Outside the cone are events that cannot be linked to you by any signal that respects the limit. That structure doesn't care whether the messenger is a photon, a neutrino, or a gravitational wave. It's the map of what can ever talk to what. If you let any influence cross that boundary, go faster than the limit in the local sense, you don't just get a bit of new physics. You get the ability to wire events so that some observers see effects happen before their causes. Different frames already disagree on simultaneity for space-like separated events. Add faster-than-light signals, and suddenly you can string together a few moves and build a loop where information arrives back in its own past. You can set up the classic paradox, a signal that prevents itself from being sent. That's a direct attack on the idea that physics has consistent states that follow one from another. On top of that, the constant that sets this limit is not arbitrary. The same number appears in Maxwell's equations as the speed of electromagnetic waves based on electric and magnetic constants you measure in the lab, in special relativity as the conversion factor that lets you combine space and time into one space-time interval that all observers agree on, in quantum field theory as the boundary of the light cone that suppresses any attempt to send usable information outside it, in general relativity as the local propagation speed for light and gravitational waves in any small patch of space-time, curved or not. And when you push on it experimentally from every direction, it holds. Lab timing of laser pulses, particle accelerators slamming electrons and protons to extreme energies, gamma-ray bursts and supernovae sending photons across billions of light-years, neutrinos racing alongside them, GPS satellites whose timing only makes sense when you accept relativistic corrections built around this same constant, gravitational waves arriving from colliding neutron stars at essentially the same time as the high-energy light. Every check says, if there's a crack in this speed limit, it's smaller than anything we can currently detect. So when you ask, light has no mass, so why is its speed limited? The honest final answer looks like this. Light speed is not limited in the sense of some extra drag holding it back. The speed you're talking about is the maximum rate at which any cause can affect any effect in our spacetime. That maximum rate is built into the geometry of spacetime, into the energy-momentum relation, into the symmetries of the electromagnetic field, and into the quantum rules that prevent signaling outside the light cone. Setting the mass to zero in those rules does not free light from that structure. It nails light to it. Massless particles have no option to go slower or faster. They exist as excitations that ride exactly on the causal boundary. Massive particles live inside the boundary and can only approach it, never reach it. Try to allow anything to go outside the boundary, and the whole structure of cause, effect, and consistent history starts to fall apart. So when you ask, light has no mass, so why is its speed limited? The honest final answer looks like this. Light speed is not limited in the sense of some extra drag holding it back. The speed you're talking about is the maximum rate at which any cause can affect any effect in our spacetime. That maximum rate is built into the geometry of spacetime, into the energy-momentum relation, into the symmetries of the electromagnetic field, and into the quantum rules that prevent signaling outside the light cone. Setting the mass to zero in those rules does not free light from that structure. It nails light to it. Massless particles have no option to go slower or faster. They exist as excitations that ride exactly on the causal boundary. Massive particles live inside the boundary and can only approach it, never reach it. Try to allow anything to go outside the boundary, and the whole structure of cause, effect, and consistent history starts to fall apart. So light isn't some rebel that wants to go infinite and gets slapped back by a random cap. Light is what you get when a field with the right symmetry is forced to send its signals at the maximum allowed rate in a spacetime that has a fixed conversion between space and time. In that sense, light isn't breaking the law of C or being confined by it from the outside. Light is the law in action, racing along the very edge of what your universe allows. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.